Hello everyone, March 12th. All right, let's do it. Zero array transformation. Given integer array, length n, and 2D array queries. LR var. Each query represents the following action. Decrement the value at each index in this range by at most val. The amount by which each value is decremented can be chosen independently for each index. A zero array is an array with all its elements equal to 0. Return the minimum possible non-negative value of k. Non-negative value of k such that after processing the first k queries in sequence, nums becomes a zero array. If no such k exists, return -1. Decrement the value at each index in this range by at most val. The amount by which each value is decremented can be chosen independently for each index. It's just you have a cap. You cannot decrement more than val, which means you can set the val to be really big. Right? If the val is really big, then you can just get everybody down to 0. And we want to know, return the minimum possible non-negative value of k such that after processing the first k queries, nums becomes a zero array. Why don't we just decrement, because the most is val, so you just decrease val, right? So you just do it one by one, and each time you decrement all of them, and then to check how many times you have to do in order to get everybody to 0, unless everybody is already 0, right? So 0, 1, 2, so 2 steps, right? So the first step you get decrement 1, decrement value after indices by, so it becomes this, and become this again. This 1, 2, 3. Right, so you have 1, 2, 3, 0, 1, 2, 3. You can decrement by 2, so you can decrement by 2, so it becomes 4, 1, 0, 0 exactly. And then you do 0 to 2 by 1, so you have a 3, so that's not possible. So this, therefore, it's all right. So what we can do is, so there is a, I think a segment tree, something like this, to make it, because you want it is just like a range, right? Give me a range, and I will make changes in this range. I do believe it's either like binary index tree or segment tree can do this very efficiently, but I feel there might be other ways as well. I don't know. So you have every single value. Okay, is there a way not to do, I mean, if you do segment tree, what do you do in segment tree? I think that's the segment tree with like a lazy segment tree. I forgot how to set it up. It'll take a while to set it up, because a lazy segment tree is handling exactly this problem, given a range, and I'll add value to it. Add value to every single one in this range. Can we use binary index tree for this? Well, binary index tree is you change one value, but this is you're changing a series of values. I mean, even we use segment tree, we can I want to try like without segment tree. Or if you don't do segment tree, what we need is to know at which step, right? At which step every single position. So you have to go through every single position, right? Every single position. And like for the first position, which ones can handle the first position? We can sort the queries, the small. Okay, so you sort the queries, and then you start from index 0. So you check how many is 0. So you can binary search that, right? So you binary search the queries. You binary search the queries. So queries is always query is always like this, right? So you have a low, you have a high, you have a low, you have a high, you have a low, you have a high. They could be the same, right? So now we have a current index. So when the index comes in, right? And index coming, I can go a lower bound and an upper bound. Okay, so we have a lower bound, we have an upper bound. So everything in between is larger or equal to current value, right? Larger or equal to the current index, and upper bound, and the smaller than, well, or smaller equal to, right? So it's a smaller equal to and smaller equal to, because this upper bound, I will point to the next one even if it's the same. So yeah, so we get these indices, okay? We get these indices, which means its index, like this is larger than this. No, hold on. What we want to find is the index such that it contains this, right? So it has to be the upper bound. Not necessarily. Not necessarily. Maybe line sweep, because it's hard to see. Because if you binary search, you're gonna miss stuff. What if we do line sweep? How do we do line sweep again? Yeah, so we do line sweep, we basically break it out and sort it. So we say 0, right? 0 will be plus 1, 1 is plus 3, and then we actually have 2 0 plus 1. 1 is plus 3. And we say 2 is minus 1 because of this, right? and 3 is minus 1, and then 3 is minus 1. I think this is a line sweep. So at 0, basically 0 position, I get 1, and the 0 can get 2. Okay, 0 position is 2, so that is done. But how many steps? One position doesn't care, and 2 position. 1 position is out of 3. Oh, 2 is actually minus 3. So it's 2, so 1 position become 5, and 2 position become 2, so that's also good. But which step? What if we put steps in this as well? So basically become 0, value is 1, and step is 0. Right, and now we have 0, value 1, step is 1. 1, value is 3, step is 2. And 2, value is negative 3. Right, and then step is 2. And then 3, value is negative 1, step is 2, step is 1. And then actually step is 0. And 3, value is, actually we can put the value at the end, is 1. So this is kind of, right, so when we go through this, and we go through this, now we saw, okay, the first position can be filled in 2 steps. Right, the first position can fill in 2 steps. And then we go for the next one. We see if it can be filled. Yeah, line sweep. Okay, let's try the line sweep method. There you go. Alright, let's do this. Might have to consult how to sort, custom sort. But maybe we don't, if we do it wisely. So by doing wisely, I'm referring to, so I'll create a new query. right? We call it line sweep. Okay, so I say for okay. So I have the queue. Now we say line sweep dot pushback. So I'll have the starting position, index, and a value. Value is gonna be this, right? And the end, so also pushback, and will be the end position. Actually, end position plus 1, negative I, I again, negative P, 0, 1, 2, 2, 2, my bad, it's 2. The value is at a 2 position, right? So we have this P. Why do you call it P? It's not P. Dude, it's Q. I don't know what you're thinking. It's Q. Alright, so we get the line sweep, right? And then what we need to do is rest equal to 0. We need an index to go through, so I have, let's call it I equal to 0 as well. And then we say for int j, do you need int j? Yes, I do. I do. So j is 0, right? And then j smaller than nums dot size and j plus plus. Okay, so what do we do? So I'm at this position, so I need to see line sweep. If it's equal to me, then I need to keep adding, right? Or yeah, we need to keep adding. And once it goes beyond me, once it's bigger than me, then we stop. So if it's smaller than me, if it's smaller than me, then we just keep adding. Isn't that just a prefix sum, if you think about it? Right? I feel like it's just a prefix sum. Right? It's just a prefix sum. So we start from the beginning, and then we just, go. Yeah, it's just a prefix sum. I forgot to sort it. Line sweep dot begin, line sweep dot end. I believe that's the way, right? We sorted, and then we'll go through them one by one, and then for each one, we basically we have the current, right? And we say while I smaller than line sweep dot size and line sweep I, it depends on it's 0. If this is smaller or equal to j, right, then we say current plus equal to line sweep I, that's actually not true. How should I make it? Yeah, so we're at this, right? Now we need to know what's the first time that it gets. So, but we do have to, just handle them all, right? So we'll say plus equal to 2, right? line sweep I2, and we say if current is larger or equal to nums j, right? If it's larger or equal to nums j, then because we also sort based on this index, I hope it go like that. So we sort first based on this, and if it's the same, we sort based on this. So what we want is the maximum, right? Maximum step. So res equal to std maximum res and your line sweep I1. Okay, and then I plus plus. And then we do it again, we do it again, then do it again. And if current the first time it's bigger, that doesn't matter the first time it's bigger, the second time it's bigger. Oh, the first time it's bigger. I think it's good enough, right? The first time it's bigger, because if we keep going, it's gonna keep recording, right? It's going to keep recording, so I don't think we shall do that. Yeah, I don't think we shall do that. We just record. So we plus that, okay? And then the next one, we'll plus that, right? And then the first time that is above, then we set it, then what? Then we need to notify that we have okay, so I have a boolean value. Reached. And not reached. That's not true. Hold on, let me think again. Minimum possible steps. And I have to do this one by one, right? Left to right. The first K queries, yeah. So you do have the first one, like it's adding this much, the second one, and the third one, and first time that it reaches. The first time that it reaches. So if this is smaller, then we don't do anything. But if it's bigger, then we shall set. Yeah. So the first time and not reached. Yeah, and then we set reached equal to true. Alright, so because we set reached is false, so each time it's smaller, the smaller. The first time it's bigger and reach is false, I check. That's not true. Okay, so I think I have to handle this every single time. Right, so basically I check if it's larger than, we set reached equal to true. Okay, so different. So we add it first, and then we check. If it's larger than, we set reach equal to true, and then we say if reached, right, then we don't. So if we have not reached, but the first time that reached, it's important. Right, it's just not reached, not reached. So we say if not reached, right? Then we say res equal to if not reached yet, then we always try to find the biggest. And if it's larger than, which means this is after we have added to the current, right? And it's larger equal to this, that means we have reached, which also means the subsequent times if it comes again, because I have to do this, unfortunately, but it has reached, right? So we don't do this, so I don't update this anymore. So yeah, we keep doing this until we hit something which is larger than j, right? And once we hit there, j will move on to the next one, right? J will move on to the next one. Now j move on to the next one. If the next j it's larger than j, so which means I need to see the current value. Right, I need to see the current value. This is to move I forward. So we're just trying to see, accumulate everything that's adding up to the current j, right? Accumulating everything that's before j. So we just we add, and then the first time that we reached, which is good, okay? But then once we're done, the next one is far away, okay? Next one is far away. So the next one come in, and it's already been done, right? So we just need to check. But how do you know how much the next one needs? Right? How do you know how much the next one needs? So like the current one, you say we add up this number of times, then it reached the level. But yeah, it doesn't feel right to me. Because there is an order. This method does not respect order. We have to respect this order. Man, really? I have to pull out the segment tree for this? I don't want to. Can we have an easier way to find after case steps? Right, after case steps, if any position, the value is still case steps, you say? Because that's the, we want to find a min max, right? Minimum k that can make it work. Can we like binary search? I'd say getting k to be half. So we go through half and try to fill out the whole thing. I'm not sure half. So you're saying the same method, but we take the first, we take like, we take a certain amount, right? We take the certain amount, break it down, then do the line sweep. And because everything is on, so it might work. Because all I need, it's something like this. Hold on, private. Return Boolean value, right? Check. And we need numbers. So that's how we use to check. Right, and we need queries. Right, and we have k. So the question is, given a k, is the first k, right? So are the first k queries able to cover the entirety of nums? If yes, return true, otherwise false. That's kind of the question that we want to ask. And we'll do this line sweep shenanigans. Right, so we do this entire thing. Okay, so we get a line sweep, but instead of smaller equal to this, right, because it's asking the steps, so just the count, right? K is steps, so it's smaller than k. Right, smaller than k. Ooh, this is another log n. Right, this is a unlog n here. We get a first k. We sorted it, right? And then all we need to know is at each position, what is the final value, right? The final value, because these are all positive values, so you will just always add them up, right? We just say in the first k, can we do this, right? Can we do this? So we do this. First case steps, right? Then we do line sweep. Then we don't care about this I. Right, we don't care about this I. What do we care about? We care the indices. Like at this position, what is the final value at this position? So, yep, so we only care about that. So we don't care about this. Now we sort them and we go through, and we don't even need the rest. So we just go through nums, everybody, and doesn't matter. We just say if I is smaller than this, and then we do this, right? We do this. Plus plus. So now by doing this, what we get is simply at the current position, what's the final value after we aggregate everybody? Right? After we aggregate everybody, what's the final value at this? So the final value at this position, then we say if nums j, right, turns out it's larger than current, then we just return false, which means we cannot do. Otherwise, we'll return true, right? Otherwise, we'll return true. So here, it becomes very clear what we want is a low equal to, I don't know, we have 0 steps, right? If everybody is 0 already, so it's just, you take 0 steps. And high is you take all the steps, right? You have to take every step. And in my method, usually I have to add 1 to the upper bound. Then we say while low, I usually do smaller than high, and mid shall equal to, I believe it's low plus high minus low divided by 2 to avoid potential overflow. Right, so we have a mid, and the mid is where we go. Now we say if, check nums, queries, and a mid. If it's true, right? If it is true, that means do mid number of steps, it's good. Then we can just go lower. Then we just say high equal to mid. Else, we say low shall equal to mid plus 1, right? Else means it's false. It's false, so you need to get a bit bigger. So we do this, and then eventually we'll get out. It's a low, right? So which means it's a false. So we need to plus 1 to get out. So I think at the end we shall return low. So this is a binary search. Not 100% sure if it's right, but we'll see. Use a line binary search with each step at binary search, right? At each step, use line sweep to find the max value that can be accumulated for each position. So it's O n log n squared, right? Because take log n on the outside. Oh, hold on. Let's do an. Okay, so it's so the check, right? The check is we'll go through the queries. Now we'll go through the K. So it's n, right? So it's n. So on n log n is inside times log n. Okay, that's how I interpret this. Let's see. See if it's correct. This is a error because I changed it. Now I don't have 2. Oh, 3. So actually gets out. Return low needs to be smaller or equal to queries size. If it is, return low. If it's not, return -1. Forget about that. All right, let's try it. So apparently this does not work because it's a little bit too slow. I'm pretty sure it's this part. So if we can make this part faster, it will be big. Can we just, do it once? And that's the thing. If you do it at once, you don't know which position. Line sweep. How about we get all of them? And then now we have a K, right? So K restricts which ones we can handle. So we just, skip the ones we cannot handle. Oh, that's actually not a bad idea. Okay, let's try this. So we just need to tweak the performance just a little bit. Okay, just a little bit. So what we need to do is let me get this one. So we'll do it only once. Okay, so we do it here. And this is not K, so we'll get everybody. So queries.size. This is the entire line sweep. And now we store the entire line sweep, but we do have to add I. Right, we have to add I. And here I need to add a line sweep as well, which means, unfortunately, here we need std vector std vector line sweep. Okay, so we add a line sweep and then we go through this depending on the K, right? So line sweep, yeah, we just need to go down. I smaller equal to j. This is fine. And we say if, right, line sweep I1 is smaller, so index, so this +1 should be smaller equal to, so this +1 should be smaller equal to K, right? So if that's the case, that means it's within the range, then I can use it, right? And I can use it. I use it by adding 2. Okay, use it. If it's larger than k, then I cannot use it because it's belonged to till later, and I just need to keep going for it. Right? We cannot use it if it's later. So we go through everything, then we check. Okay, let's see. Let's see how this one goes. It requires us to be a little more performant. And let's use this test case and see if we can get this little bit of performance in. Oh, feel like that feels like a different problem because we cannot even handle the first one. I wonder what was the problem. Ma 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 ma. Yeah, I think this plus plus has to get on the outside. There we go. So, better performance. Yep. Doesn't matter. Good, bad. 800 millisecond. I'm happy. You know, we got this one. And then we should read the document to see, basically just to see why it's so slow. I mean, we know why it's slow because we used the binary search for this, and it's, you know, it's kind of slow, and we have tweaked a little bit to get the performance up. So what is the, please don't tell me it's, okay, we have binary search, but maybe that's different from the way I do it. That seems to be, don't know. Line sweep, isn't this our method? It can do a linear. Oh, shoot. Oh, damn. This is wrong. Ah, screw you. Screw me. This is wrong. Shoot. So, we start by the queries. Okay. The queries, so we call it m log m, is for the queries, and then, well, plus this is log n, and then we do n log m. Yep. Where n is len nums and m is len queries. Yep, that looks about right, which is the first solution. Right, well, I call it line sweep already. So what is this magic? All right, let's just read the code directly. Difference array. Okay, difference array. Iterate through nums, iterate through queries, while current index of num cannot equal 0. Well, sum plus difference array is smaller than num's index. 0 array is informed after all queries are passed. K is larger than, what the hell is K? K is 0. K is larger than this. Okay. So we iterate K's forward. Difference array. Left queries That's just index. That's another index as a value. Okay, so we get a 3 value. Process start and end. If right is larger equal to difference array plus equal to val. Difference array maximum left and index. Left and index. Difference array right minus. Okay. So we externalize the position. We externalize the position difference array at these positions. So at left or index, the maximum of the two. Either index or left. So we go through this difference array index. So at each position, I process this difference array, right? We basically just keep adding to it. And if it's this, then it hasn't reached it, right? So we keep going. So at a certain point, it will reach, then we check. And we update the prefix sum at the current index. Yeah, we add the prefix sum. Basically, that's the sum. That's what's cumulatively we have done so far. I see what this is. It is line sweep, and I have seen this technique before. It's not the first time I see it. I've seen it before, but it requires some practice to get it. So essentially, when you have this, right, and you have these queries. Now we only consider query starts and query end. And the reason that in my line sweep, I order everything because I do it sequentially. I don't consider jumps. Because when you sort it, you don't really have jumps. Everything just follows a certain order. But that requires breaking down of the original queries into this line sweep array, and you have to do a sort, and that takes time. Usually you can swap time with space. We just need more space. I mean, technically we did use more space here as well. So you use a space to keep track, right? To keep track of what each position is, like what each position, the value, the difference value, the delta at the different positions. That's actually make me realize delta is a better term for this. Okay, so this is the same, right? We can say that this is also line sweep, but much better implementation. It is from the editorial. We use a delta array to keep track of the delta value, right, at each position, right, at each position mentioned in queries. And as we go through nums left to right, we use the delta value to compute the current, right? To compute the current max, the current max value accumulated for each position, right? And then whenever something's bad happens, then you just cannot do it. But if something good, so how do you keep track of the, how do you keep track of which position? You don't have to keep track of which position. You go through this one by one, right? You go through the index on nums one by one, and for each position, you also go through the queries. Now you go through the queries, and you keep track of which value you're keeping. Yeah, so basically we have int, we call it, let's call it k, okay? So k is 0, which is for the queries. And you also have a vector of just int. I'll call it deltas, and it has to be of size, because what we want is to keep track of every single position. So it should be nums.size, right, at every single one. So everybody start from 0, I believe. And then we say for int I, 0i smaller than nums.size, I plus plus. Okay. And then, given this, we have to, we have the current, right? So we do a current shall equal to 0 as well. So k, right? And we need to process it first. So we say k. So we keep processing, right? We keep processing until we can't. So we say while actually we say if k, right, is already equal to queries.length plus size, return -1, right? So that means exhaust queries, but still cannot cover all nums, right? And then we say while this is smaller than queries.size and queries k, right? K 0 is smaller or equal to the current I. If that's the case, then we say deltas I believe it's just go k 2, right? And then deltas queries k 1 plus 1 minus equal to queries k 2. Okay, and then k plus plus. Right, so to the next one, we try the next one, we try the next one, and each time we will add to the current because they smaller or equal to I, and then since they smaller or equal to I, we always can add them. So the start is smaller or equal to I, right? But just the start smaller or equal to I? And we trying to get, like, the first one will have like the 0 add and a 0 add, and next step it's too big, so we jump out, so we find, okay, 0 is fine, and then 1 comes in, start is too big, right? So we don't do anything, then we just use the current, and then 2 comes in, and we'll use the current, so yeah, whenever we find beginning is smaller than the current, right, we can always accumulate. But my question is, you say the beginning is smaller, but what if something comes, beginning is smaller, but end is also smaller? Is that possible? It's not possible because your previous one should have already consumed it, right? Because the previous one must consumed it. So when you come in, it will always be because the I is sequential, right? I is sequential. So if we have something and then we consume everything that the start is smaller than this, okay? So the next one is actually bigger than it. So when you come in, either you don't get to do it or you will be on that thing. Yeah, I think this one should be fine, right? This one should be fine. And then once at the end, I shall say current plus equal to delta I, just to see if there are any negatives, right? Any negatives? But nothing is sorted. Okay, I forgot. Let's check back. What was it? Oh, that's very different. It's sum plus delta index. Sum is the cumulative one, right? So it plus delta index. And if it's smaller than nums index. Okay, sum is the cumulative so far. So we add the current. If it's smaller, then we need to move forward. And then we move forward, you just go to the next one. So we will add this. We'll process. This is the key, right? This is the key, okay. So, you know what? I think we should do this one more time. We should do this one more time. Well, I'll keep the majority, but this is just gone. So yeah, it was not right. So basically, what we want to do is at each position, right? We know add the cumulative, which is the current. We add it to the delta to get what the current one is, and we compare, right? If it's already larger or equal to the required the number, then it's good. We can move on to the next index, right? We can move on to the next index. And if we add to it is smaller, then we need to move, which means it's not enough, right? It's not enough. Whatever the cumulative plus the delta at the current position, you add them together, it's not enough. So you need to move the queries forward. So you check the next query. Now when you check the next query, you have a query beginning, query end, right? So if the query, I think it's the query end. No, it's query beginning. If the query beginning is smaller than the current index, or maybe the query end. No, if the query beginning is smaller than the index, yes. If the query beginning is smaller or equal to the index, then whatever value it is can be applied directly to to the current index. So you just add to it. You add to the sum, right? You add to the accumulated one. You also need to update the end, right? Update the end. Let's just check one more time if that's the right. Oh my god, that's not right. If right is larger equal to, now this we agree. This right is larger equal to index. Well, right is larger equal to index. What if the left? Oh, the left does not matter. The left does not matter because I use this delta array to update. We always update the delta array. We always update the delta array. It's just which index we update. So the right, if it's larger or equal to the current index, then we definitely update the right. But at the same time, we have to update the left, or it's the maximum of left or index. Right, the maximum of left or index. Yes. So update that, and you could update the index, or you could update the index. That just means update the left. That just means we haven't reached that interval yet, right? So we do this. We come back up, and we check. It's not working. We come back down. So eventually, at a certain point, it will work. Then we'll break out that sum plus equal to index. Man, this definitely require more work on this. And this delta need to be +1 because we need to get delta n plus 1. Yeah, delta n plus 1. This has to be +1. You know what? Don't do it. Let's delete everything. Clean sheet. All right, clean sheet. So let's do this one again tomorrow. I think it's worth it. The line sweep method is very smart. I have used it in interviews successfully more than once, so it's important to go through this again and just practice. More practice on line sweep. All right, that will be it. I'll see you guys tomorrow. Adios.